Now, all the K's we've written so far are called K sub C, and K sub C is by far the most common equilibrium constant. The little c there stands for concentration, and concentration in chemistry is almost always moles per liter, the big M. However, you can have what's called a K sub P, and KPs are gas equilibrium constants. Now, if you're using a KP, you have to use atmospheres for gases, all right? And 760 millimeters of mercury equals 1 atmosphere, if you remember from Chem 222. So if you're dealing with gases, you can use KP, no problem. Just make sure all your pressures are in atmospheres. So here's an example of a reaction that you could write as a KC or a KP, depends on how you want. All the reactants and products are gases. So a gas can have moles per liter, like in a flask, that's no problem. But you could also have the individual pressures of the gas. So a KC for this reaction would be ammonia squared divided by nitrogen divided by H2 to the 3rd power, and that's totally cool, and that's probably how we'll write it most of the time. However, if you had just a bunch of atmospheric pressure data, Kp would be the pressure of the NH3 squared, and you would divide by the pressure of N2 and the pressure of H2 to the 3rd power. And again, all those pressures have to be in atmospheres. So use the one that's easiest for you. Most of the time, Kc is great, but if you have a Kp, no problem too. If you have a Kp and you need to turn it to Kc or vice versa, you can use this expression right here. Kp equals Kc times RT to the delta N. So T is temperature, the Kelvin temperature of your system. R is the gas constant R, 0.082057 liters atmospheres per mole Kelvin. And then delta N is the change in moles of gas. And you only look at the gas. You don't look at the solids, the liquids. You don't even look at the aqueous parts on this. So delta N, products minus reactants for gas. So for the ammonia example we just did, delta N would be 2 for the products, 2 moles of gas, minus a total of 4 moles of reactants. 1 nitrogen plus 3 hydrogen is 4. So delta N would be 2 minus 4 minus 2. And you could plug that into delta N at that temperature, the gas constant. You can turn your Kc into Kp, no problem. Delta N can be positive and negative. It can be 0 as well, where Kp and Kc are the same. But more often than not, there's a slight difference between Kp and Kc, so that's where this all pops in. So the question here is, what's the delta N value for this reaction? And we have here ammonium sulfide breaking down into ammonia and H2. So delta N is the moles of gas as products minus the moles of gas that are reactants. And you can see here we have 2 NH3 and 1 H2S, so that's 3 moles of gas. But on the reactant side, we don't have any gas, so that would be 0. So for delta N here, it would be 3 minus 0, 3 moles of product gas minus 0 moles of reactant gas. Delta N is going to be 3.